these are in kip feet?
Yeah. My units for all my numbers are in kips and feet. So unit of moment is always kip feet, unit of length is always feet, unit of force is always kips. I'm just saving writing the units down everywhere because it would get very tedious really quick.
And those are given moments.
Yes, these are the capacities we determined from the moment curvature analysis and the plastic hinge length of each of these columns.
Is that 974 times?
Yes.
17.86?
That's really awesome. Yes.
I forgot to ask, your sign convention, what are you taking to be positive and negative? Positive is clockwise? Negative is counterclockwise? Yeah. Or is it depending on each? Okay. Okay.
My sign convention. European students in here may be familiar with the flip sign convention for moments. America and Europe like doing things backwards. Each has its merits, but it's not like one way is wrong. I stick with the American sign convention. So this comes from here, dead load. So those were the moments used up by the dead load of the structure. What you see here these came from the first push. So we had a scale factor of 17.86 before in order to form the first hinge. And in doing so, not only was that first hinge formed, but we used up capacity of the other hinges as well. So how much was that 1786, or that 17.86 scale factor, times the unit moment for each of those joints from the previous step? So if you go back to our chart, a couple pages back, you would have seen that the unit moment, the 100 kip unit moment for joint B would have been 974. And the 100 kip unit moment for joint C was 788, or 798, sorry. So these were the unit moments from the previous push through both of these joints, multiplied by the scale factor from the previous push. So as we push this guy over, we used up all of joint A's plastic moment capacity. But as we were doing that, we were also loading these joints with additional moments. How much moment? That scale factor times that unit moment from that 100 kick push.
Scale factor 17.86 is from.
That was from the previous push. That's how much scale factor it took in order to form the first hinge at A. So as we applied that first lateral load, we found that a scale factor of 17.86 formed the first hinge. So if we look at that table, we had a bunch of different scale factors. Hinge A had 17.86, hinge B had 25.74, hinge C had 22.56. So we picked the lowest scale factor because that's what's going to form first. And so I'm using then that same scale factor, but I'm scaling now the unit moments from the other joints by that amount, because this is how much moment developed from that first push in the other joints.
Then how do you get the 1365?
So 1365 comes from this 1.44 scale factor times these guys right here.
So you're reducing the demand, the plastic moment demand by what we previously scaled it up.
I'm increasing the amount of demand on the joint, is what I'm doing, based on the first push.
Increasing the demand on the joint.
Yes, the demand increases as you push this frame over more and more.
So it's getting more negative, but that in this case is essentially.
The negatives and the positives are just a matter of direction of the moment.
Okay, gotcha.
The capacity of the moment is the same in either direction. I'm just making sure I define things correctly based on my sign convention, because remember we said that in this case we had dead load helping the structure.
Yeah.
So depending on which direction you're going, those initial moments may not necessarily be increasing demand on the structure against that lateral motion. Maybe actually be helping you. Because if that joint flexes the opposite way, and you have to push it this way, you have to overcome that initial rotation the other way before you can start loading it in the direction towards failure. So that's the big important reason to keep track of the positive and negatives. Not so much of the positive negative on, let's say, the capacity of the joint. Just making sure that the directions of your moments are consistent with your push. So as you're pushing it over, you want to make sure all your directions of your moments are consistent from all your different load cases through all your pushes. So I use this sign convention to come up with the positive and negative for everything. So what we find then from this analysis is our next hinge forms at C. So once again, we want to go through the steps and come up with the displacement capacity of the frame up through this point and the force capacity of the frame up through this point. So we're interested in the force versus displacement behavior. And if you recall, our very first push, we come up with something like this. And so what's going to happen now is, well, this stiffness was the elastic stiffness of our frame. After we formed hinge A, we had the frame soften. Let's say we're going to go up to the next point following a softer stiffness. So let's say this would be then K1. The next stiffness we're interested in is K2. And why this is of interest to us, beyond, let's say, a strictly design point of view, is if you recall from the very beginning of class, we looked at the average acceleration method. We looked at the equation of motion for a single degree of freedom oscillator from, let's say, an acceleration profile from an earthquake. Part of that response was based on the stiffness of that oscillator. We can just as easily model this frame as a single degree of freedom oscillator by saying it just has one translational degree of freedom. You can say the rotational degree of freedom is minimal. You could also include the rotational degrees of freedom. But if you're doing a very simple analysis, we could just look at the translational degree of freedom in this. And we could use the stiffness of the frame, depending on what branch it's in, to come up with the equation of motion and the dynamic response of this frame for a full nonlinear response. Once we can develop this full force displacement response, we know the stiffness at each of these branches. And once we know the stiffness at each of these branches, we can do, let's say, a full nonlinear analysis using the equation of motion. So that's what makes this really powerful. And that's kind of the correct way to do earthquake engineering if you're looking at it from that point of view. When you're doing, let's say, a full dynamic analysis, you're developing basically the force displacement response of the system as a whole, looking at each of the nonlinear events. And once you have that adjusted stiffness, you can use that adjusted stiffness in your models each time step in order to solve the equation of motion. And so then you can come up with, let's say, the full response of your structure and check to see if it stays within capacity from an earthquake demand using, let's say, the full nonlinear performance of the structure. Instead of using, let's say, the equivalent force procedure, where you're doing everything on this equivalent elastic modeling, which we said has lots of problems. So you can take all the stuff we're doing here, and then you can apply it to the dynamic side of things, which you can take from a structural dynamics course, and do lots of more robust things with it. So we're interested in then the force and the displacement associated with this next step. So previously, when I came up with the displacement of the frame, I was interested in looking at, let's say, member AB. I believe that's what I did before. Looked at this member AB, and I can get the displacement of this guy by itself, and that gives me the displacement, if I look at the top of that, of the frame. The problem is now we have a pin here, which means I can't just look at this kind of as an individual cantilever. I don't have multiple boundary conditions known. Before we knew, let's say, the rotation and the displacement at this boundary condition, or at this end condition here. For a fixed member, you have no rotation, so I knew the rotation was 0 at that end. And I also knew the displacement was 0 at that end. But now, because this is a pin, I don't necessarily have that information offhand. So instead of just going directly to one of the columns to solve for the displacement of the frame at this interval, I have to first look at the beam. So I look at the beam by itself. two-body diagram looks like. So,
Tim,
yes.
is there a reason your moments at C are
Yeah.
going in the same direction?
Which is,
They're both traveling clockwise.
yeah.
The reason is I drew it wrong. Yes.
Okay. I think you may have done that last class as well in one of them. Is that intentional or not intentional? Okay.
So I'm going to look at the sum of forces in the y. I'm interested in what these guys are. Find that these reactions are equal to one another, which is what we expect. Take moments about C. Take moments about wherever you like. Once again, I'm interested in coming up with the displaced shape of this guy. You're welcome to use whatever method you feel is appropriate. I did double integration once again. So I'm interested in the boundary conditions for this beam. Now displacement at the joint ends here is going to be 0, just by nature of the fact that they're my reaction points for the beam. So stating that mathematically, I'd say at x is 0, y is 0. That would be corresponding to this boundary condition at B. If I plug x's 0 into here for y is 0, I have 0 is equal to 0 minus 0 plus 0 plus c2. I can reason out that c2 is equal to 0. Which you recall makes sense because c2 is related to the displacement at your x equals 0 point. And in this case, I have a reaction point from x equals 0 location, so I should have c2 at 0. My other known boundary condition is at C. This distance here.
50.
Oops, that's 50. 30. So when you're doing this, I recommend definitely keeping track of your units, especially when you're looking at E and I, not always in kips and feet. So I left units out here, but in my notes I have units next to every single input. So this is one of the big parts where you can make significant unit mistakes if you're not very careful. So the 50 here is in feet. This is kip feet. Kips. And if you solve for C1 now, you will find that C1 minus 9125. So why am I doing all of this? I need a boundary condition to go with the column. Because I only know one boundary condition here. I know that at this base, at point A, I know the translational displacement is 0. Outside of that, I don't know anything of use. So I need a second boundary condition. And the way we get a second boundary condition is I can look at the rotation of the beam, and I can associate the rotation of the beam to the rotation of the top of the column. So I'm going to be interested in theta then at x is 0. You could also do it the other way around. You could solve for theta at your 50-foot location, and you could use, remember, CD to solve for the displacement of the frame. Because then you'd have two boundary conditions on this column as well. Either one works. I just went with AB for consistency. And it's also easier because you look at the x is 0 location, you go up to your slope equation. If x is 0, both these terms drop out. You're just left with C1 is equal to theta times EI. So solving for theta at x equals 0, it's just C1 divided by EI. So this is what I was talking about with the unit mistakes potentially. Make sure I converted E from KSI into kips per square foot. And I find that theta is 0.0007921 radians. Negative, which means downward rotation here. What's that angle?
I2 at
20. I believe we said I was 10 feet to the fourth, and I of the beam was 2I. Oh, 20 feet to the fourth. So then I can associate the theta at the top of the column with the theta at this end of the beam. These are going to share rotations, right? This joint can't have two separate rotations between the beam and the column. So whatever rotation is caused by the beam is also going to be rotation at the top of the column. So this gives us another known then for this column. We now know that the displacement at the base translationally is 0, And we now know the rotation at the top of the column is equal to that many radians. So now we'll move the analysis over into the column. Just to help you visualize that, that's the rotation actually. If you were to draw the deflected shape of this beam, the rotation at the end would be that much. Using statics, we know the moment over here is 1365 kip feet. The length of the column is 30 feet. You can easily solve for RA. And as RA is known, I can easily get the moment equation for the beam. Once again, I solve with double integration. The choice is up to you. Again, to solve for C1 and C2, you're interested in the boundary conditions of this beam. We know that the translational deflection, if the reaction point there is 0, so I can say if x is 0, y is 0. Once again, we'll find that C2 is 0, which again makes sense because C2 is proportional to the deflection at your x equals 0 point. If you have a reaction at your x equals 0 point, you will have a reflection nearby at all. But before we said, well, the rotation at that location was 0, we said dy dx was 0 because it was fixed, but now we no longer have a fixed point there. And so for our next boundary condition, we want to make use of the fact that we solved for the rotation at the end of the beam. And we'll say that x is 30, dy dx is equal to that. So we do a little algebra. We plug 30 in for x here. We plug 0.000791 radians in for theta. And we're going to keep E and I in there. We can solve for C1. For all that work, we can find out that C1 is minus 24,125. And so I can then solve for the displacement at 30 feet, because that's what I'm interested in. After all that work, I find that the deflection of the frame is 0.1126 feet. Down in this case on the column, that's just the way we oriented this, but it makes sense because we've been pushing the frame to the right. So if we look at this column right side up, a direction of down would be a displacement to the right.
So why don't you say right? You're pushing the frame. If you look at
Because I'm being consistent with the way I drew it. But yes, it corresponds to displacement push to the right. However you want to keep track of it in your work, by all means. I just like keeping track of things locally to whatever space I'm working in, and then I can interpret it from there. Because I turned this column from vertical to horizontal, I'm just keeping everything consistent with that diagram. We're not quite done with this yet. Before we move on to the force displacement diagram, there's also something of use to us here. And that is, as we've been doing this second push, and we're increasing the lateral force, joint A formed a plastic hinge, which means it started to rotate. And as it started to rotate, the more lateral force we apply, the more rotation generates in it, and the more of its rotation capacity is expended. And we're interested in now how much rotational capacity has been expended from this push. So we can go back then to the slope equation, and A is located at the x equals 0 point. So if I find the slope associated with x is 0, I know the rotation at joint A. Once I know that, I can start factoring that into my calculations.